To continue our tutorial, first of all, thanks for coming back. And so before the break, we start a little bit on the distributed optimization, and we basically assume each machine has a data set, SJ, and they can create this local problem, which is exactly the same, has exactly the same formula as the original problems. And we mentioned that if you just let a local machine solve their machine learning problems using their own data and generate a solution and just simply averaging them, and this algorithm doesn't work. No matter how many times you do this, you never converge to the optimal solution of these global problem. So the conclusion is that the rising to average is not W, this parameter W. Instead, the rising to average is actually their gradient. You let each machine sample a data within their data set and calculate the corresponding stochastic gradients on the same point, Wt minus 1. And averaging them, you get a so-called mini batch stochastic gradient. Okay, so doing mini batch, it helps to reduce the noise in the gradient. So you update the current solution along these mini batch stochastic gradients. And here is the, well, before I introduce the performance properties of these mini batch SGD, so we said that in the distributed optimization, we care very much on the rounds of communications. We also care local runtimes, but the route combination is sometimes the bottlenecks in the performance of the algorithms. So let's look at this simple mini batch. In this framework, in this methods, what local machine does is not optimization algorithm. It's just calculate a gradient. It's basically matrix vector multiplication, essentially. So basically, the local runtime is O1. You may say it's OD. Yes, it should be OD because it depends on dimension. But here, I hide the D within this big O. The reason is that all the complexity result in this part will depend on the dimension D anyway. So I don't want to write so many D's everywhere. So I just hide it in the big O. So here, essentially, it tells you local runtime is big O1 because every machine is only evaluating the gradient of one data point. So it's O1. And it's done in parallel, so it's O1, not OM. So here, communication time per rounds actually also depends on number of machine in these distributed optimizations. The communication time per round is how much time it takes for this machine to send, for example, to send this gradient to the center or send something between each machines. Okay, so I don't want to make a conclusion about the dependency of these communication time on the number of machine because it really depends on network engineering and how do you really implement it. It depends on the system. It's already beyond optimization, beyond machine learning. So I don't want to write a kind of complexity here because it's not complicated. It's not simply OM or square root or log M. It's not. It's nothing complicated. But what we know is that, of course, if you have more machine, the communication time per round will increase. So we only know it's monotone, but we don't know any specific formula. So now let's talk about how many rounds of communications, which is something we care about. How many times we need to basically average these stochastic gradients in order to guarantee epsilon for the global problem. So here is, when the problem is strongly convex, we have a 1 over m lambda epsilon. So 1 over lambda epsilon is exactly the same complexity of the stochastic gradient descent if you have a strong convexity. However, here we have m here. It means that if you have more machines, you need fewer communication. Fewer rounds of communication. But at the same time, you need to more machine will increase the communication time per round. Okay, so there is a trade-off there. And if the problem is not strongly convex, everything is the same except the epsilon is now epsilon squared in the denominator. So you really need more communications. So you can see that in single machine cases, algorithm prefers strong convexity to non-strongly convexity. In distributed case, the story is the same. If you have a non-strong convexity, you really need to communicate more. And now, how do we choose number of machine? It's easy. So if you if a local machine is very fast, you want to use fewer machines. If your local machine is very slow, you want to increase the machines. There's a trade-off actually here. You can see when m increase, rounds of communication decrease. But at the same time, this blue part will increase. So you have to balance it by yourself. Now let's talk about another one which is more complicated, more sophisticated than stochastic gradient descent. It's called a distributed SDCA. I cover SDCA in the first part in the single machine cases. Then what is this exactly is a distributed version. It has been first discovered by Tianbao Yang and also studied by other literatures regarding the improvements on the theoretical communication complexity. So for simplicities, I use lambda 2 non-square, but it works actually for others. But here we want to make it simpler, so I actually use lambda 2 square with lambda greater than 0. If lambda is 0, actually it doesn't work, unfortunately. So here is the global dual problem. Remember, this is the dual problem we formulated before using this conjugate duality. The difference is that we have capital N, of course. Now we have, as I said before, you have one dual variable corresponds to one data point. And here is the similar, it's exactly the same situations. We have capital N data, so we have a capital N data point, but we partition the data into subset S1 to Sm. So we can also partition this dual variable just as we partition the data, right? So we get a partition of alpha. So here is alpha S1 are not a scalar, it's still a subvector. So each machine is not solving the one block of the dual primal problem. Instead, each machine is solving the one block of the dual problem. So we call it local dual problem, right? So you can see this distribution variable is only over alpha Sj. It's a kind of the problem of is the problem you can obtain if you're fixing all the other variables except the variable corresponding to the data in machine J. Okay, so we can use exactly the same trick as before if we introduce the primal variables, which is still in the same formula as the single machine SDCA. We still need this dual primal variable such that each local problem can be simplified. And another trick we need to do is you do the changing of variable. Instead of talking about what is the optimal alpha, we talk about what's the optimal difference between the next alpha and the current alpha. After using these two techniques, we end up with this a problem which is a little bit easier to optimize. So we don't need to worry about how to optimize this block of alpha corresponding to the data set in machine J. Okay? So what we do is that you can use whatever algorithm to solve this local optimal. It does not have a closed form, unfortunately, because it's not in R1, it's in Rn. But you can use any algorithm to solve these local problems. So I run so this is not exactly output, but it's approximate optimal solution. So we obtained delta alpha, which is the approximate optimal solution of these problems. I will talk about how this accuracy of approximation affect the rounds of communication later. So here, we update alpha according to the optimal outputs from this solver, local optimization solver. And we also need to update this W, which is the difference in this primal solution. Okay, we update a change in the dual and primal. What we do is that each machine runs these local problems and calculate this delta W and send it to the center. When the center receives the delta of W, they add these delta together and we update the delta. We update the W. So each machine suggests a change in the primal problem, although they only solve the dual. And the center collects the change suggested by each machine and aggregate it. So this is distributed as SDCA. It's also known as Discrete in the Young's papers and also Cocoa Plus. So these are actually equivalent algorithms. So now let's talk about how much precise we want to solve the local problem. You don't have to solve the local problem to optimality. Actually, you have to take an infinite amount of time to solve it until you get an optimal solution. But we want to stop at some point. Here, we write these local objective functions as this G, delta alpha, and WT, because it depends on alpha and W, and both primal and dual variables. And here, we introduce this theta. So left-hand side is the optimality gap, how far you are away from optimality when you return the local solver. And the right-hand side is the initial optimality gap. Theta is something less than 1. Usually it's a 0.5. You want to reduce the optimality gap by 50% and stop. You don't have to reduce it until you go very close to local optimal, because your goal is not to solve a local problem. Your goal is to use a reasonably good solution from a local solver to help you improve the global solver, right? So here, theta is usually choose as 0.5 is good enough, but sometimes it allows theta to be something even bigger. Now let's talk about the property of this distributed coordinated sense. Here is the local runtime per rounds, assuming you use SDCA to solve the local problem. So the global problem is called distributed SDCA, and the local problem is solved by SDCA without distributed. So here, it depends on theta. If you solve the local problem to very precise, you spend a lot of time in local server before you commute, which is not good, of course. As I said, theta is usually 0.5, so this term you can consider it as a constant. So local runtime is actually this much. M is the number of machines, so if you have M more machines, local machines don't have to run very long. You can stop it earlier, okay? And if you look at the rounds of the communication for this distributed SDCA, it's log 1 over epsilon. This is a linear convergence rate, very good. And 1 over lambda here. And here, we can see the theta. You can see if theta is very close to 1, this term explodes to infinity. So you cannot just give a very bad solution. You don't have to give a very good solution from the local solver, but also you don't want a very bad solution because otherwise you will need many rounds of communication. So you can see there's a trade-off. If you have a small lambda, you spend more time in local machines, but you have a very big theta, you need to run more iteration, many rounds of communications. And this is the result when you have strong convexity. What if you don't? This is the result when you have a smoothness. You always require strong convexity, sorry. If the problem is smooth, you have this result. If the loss function is non-smooth, like SVN, and you can see the dependency is a little bit different. This term becomes 1 over theta. The local runtime depends on theta in this way. And the rounds of communication become 1 over epsilon. So we go from the linear convergence rate to sublinear, unfortunately. But the dependency on theta and the trade-off between the local runtime and the rounds of communications still stay the same in the same way, right? So it really up to you, depending on what kind of the power of the machine and power of the clusters, you need to decide what is the best local precision and how many machines you want to use, basically. So if your machine in your network is fast, but the network is very slow, then use small theta, which means that you want to solve the local problems to very optimal, and you want to use as few machines as possible. As long as they can store the data, you want to reduce the number of machines you need. However, if the network is very fast, right, but the local machine is not that good in terms of computation abilities, then you don't want to solve each machine to very optimal because it will require a lot of time, and you want to use as many machines as possible. So of course, ideal cases you want to use have both terms very fast. Like you want to have a faster machine and faster network. But if that's not ideal case, these slides actually give you some intuition about the choices, the way to decompose the problem. So okay, so I will briefly go through the remaining algorithm. First one is called Disco. Previously, the dual SDCA's communications does not depend around M, if you can see this slide here. There's no M here. So machines doesn't change, number of machines doesn't change routes of communication, but for Disco, this algorithm, it really depends on number of machines. Well, the idea is that they use second order method to calculate the optimal solution for the global problem. What is a second order method? You need to use the Hessian information rather than the gradient, the second order gradient, basically. Okay, what we do, let me just quickly go over the details because I want to save time for the next part for the randomization algorithm. What we do is that we need to calculate a so-called Newton direction. Suppose you have a current solution, you construct the Hessian, you want to solve this linear equation. And this is VT satisfying this equation called the Newton system. And you go along this Newton system. This is so-called a second order method. However, it only works if the data size is large, over 1,000. So only data dimension is small. If its data dimension is greater than 1,000, it's too costly. So people introduce an alternative called inexact Newton. So you calculate a VT, which is satisfy this equation with epsilon precision. And it turns out that this VT can be found using iteration method, using matrix vector multiplication method, so-called conjugate precondition conjugate gradients. And if you look at what, sorry, let me skip this. If you look at what Disco does, is that it evaluates the solution, VT, and send it to each machine, and ask each machine to construct the layer Hessian, and then multiply it to this V, and send this V, add this V together, and do some preconditioning and send it back to the first machine. So first machine get a new V and send it to each one. Each machine is only used to calculate the Hessian, and the Hessian multiply VT. And eventually we end up with the following result. If you use discos, and you use and the rounds of communications is mu over lambda log 1 over epsilon. Mu is what? Mu is actually a parameter related to the preconditioner. So there is no clear way to choose what mu is, but usually mu is chosen as m over square root of n. The number of machine divided the data size, take the square root n. And the trade-off is to say, faster network, you want to use small m. Faster network, you want to use more machines. Faster machines, but slow network, you want to reduce the number of the machine you want to use. And there's another technique, it's called distributed SVRG. I mentioned SVRG before, and this is actually the simple distributed idea. So let me use this graph to summary. You just calculate the variance reduced gradient and the averaging length, and basically distribute the variance, stochastic variance reduced gradient back to each machine so that we can support the local SVRG. So here is the result. The first machine run SVRG up to some iteration, up to some steps, and send the solution to the second machine. And the second machine run SVRG, generate a solution, send it to the third machine, and so on. So, but this reference point, gradient in the reference point, is calculated distributedly, because this is the most time-consuming part. But this local, this stochastic step is not calculated distributedly. It's actually calculated seriously. Okay, so here is the result about the rounds of communication for DSVRG. It's 1 over lambda r log 1 over epsilon. What is r? R is the capacity, memory capacity of each machine, which is in addition to the data size S. Suppose you have Sj in the machines, and R is the number of data points you can store in addition to Sj. So here, this result is nicely connecting the machine memory capacity to a rounds of communication. So here, let me summarize the results here. We have different algorithms to handle different situations. If your problem is non-smooth and non-strongly convex, unfortunately, this is the worst case, as I said. You don't have any good properties, then you have to use mini batch as the SGD. If problem is smooth but non-strongly convex, you can use DSVRG. If the problem is strongly convex, non-smooth, use a distributed SDCA. And if you have both property, you can either use a DISCO, the second order master, or DSVRG. And if you want to make a choice between DISCO and DSVRG, it really depends on the lambda. The rule of thumb is that if lambda is less than 10 raised to -5, you use DISCO. Otherwise, you use DSVRG, because DISCO has a better dependency on lambda. Okay, so here is the existing systems or tool-pack softwares that supports some of these algorithms in this tutorial. Patterns, I think, is a distributed optimization machine learning framework, which is introduced in a tutorial parallel to this one. Is in the other room in these buildings. And Apex Spark is also a kind of architectures you can use to do different parallel learnings. And what I want to mention is the last one, BIRDS. It's actually written by Tianbao. You can download these softwares that can support on this distributed learning for a lot of loss function, hinge loss, square loss, and so on. And it's very easy to use. And there's an introduction in the same websites. Okay, I will leave the rest of the part to Tianbao. He's going to introduce randomization techniques for big data.
Okay, thanks to Qihang for the second part about optimization. Since we still have the third part to cover, so Qihang doesn't cover too much about the last two algorithms. But we will be both around, so if you are interested, you can talk to us offline. Okay, so the third part is about randomization. And in this part, I will talk about randomized dimension reduction algorithms, and then talk about randomized algorithms for machine learning and data analytics that we use these randomized dimension reduction approaches. Finally, I will conclude the tutorial with some remarks. Okay, since as we talked at the very beginning that many machine learning and data mining are formulated based on data matrix. So if we have a big data, so we have a large data matrix, right? So the idea of randomized algorithms is actually approximate a big data matrix with a much smaller sketch, okay? By either reducing the number of rows or reducing the number of columns. But actually here is that we try to explore the property of the data. So if the data contains many redundant information, we can reduce that redundant information for the safety of cost, right? So this is the framework of randomized algorithms. Actually, this is the traditional algorithms. So traditional algorithms, you're based on the input data X. So you design an algorithm, and they output a model, right? But here, we want to solve the problem very efficiently. So using the randomized algorithm, the first step we want to do is we reduce the size of the data matrix. So we're going to talk about the randomized reduction approach to reduce the size of data matrix. And then we design an algorithm that takes the reduced data, X prime as input, and output a model, which is model prime, okay? So in most cases, the algorithms A prime here is pretty much the same as the original algorithm. And here we want to show you that finally we want to guarantee that the model we obtain from the smaller sketch is very close to the model we obtain from the original data. So there are three components I want to talk about. The first is the randomized reduction. The second is the algorithm A prime here. The last is the guarantee about the model we obtain from the smaller sketch. So first for why randomized dimension reduction approach? Actually, there are many dimensionality reduction approaches. There are, for example, principal component analysis, LDA, and others. But here I want to mention that for randomized dimension reduction is more efficient and it's more robust. So if you know about the deep learning, so in deep learning there is a technique called dropout, which is actually kind of randomized randomization there, and actually leads to a more robust solution. And also, randomized algorithms give us formal guarantees, and also it can let us to explore parallel algorithms to further reduce the computation time. So here I want to talk about three algorithms approaches for randomized dimension reduction. The first is the Jensen-Lindström transform, and second I will try to generalize that to subspace embeddings, and finally talk about another randomized dimension reduction approach, which is called column sampling in the literature. Okay, so I want to start with a very famous lemma called Jensen-Lindström's lemma, or JL lemma, okay? So this is a little bit longer, but you can focus on the red parts. So the lemma says that given a fixed vector, x, with d dimension, there exists a distribution of matrix A, which is m times d. Okay? So if you apply the A matrix to vector to reduce this size of the vector, d to m, okay? So it's guaranteed that the Euclidean norm is well preserved. Okay? So if you compute Euclidean norm after transformation of A, Euclidean norm square, and compare to the Euclidean norm square of the original vector x, so you will see that the difference is very small. So it's bounded here. It's bounded by square root log of, so this is the with high probability 1 over delta. And this is the log of 1 over delta divided by the value of the reduced dimension. So in other words, if we want to maintain this Euclidean norm within our epsilon accuracy, so this is the value for the reduced dimension. So this is log 1 over delta divided by epsilon squared. Okay. So this JL lemma has very important implication. So let me tell you. So here in machine learning and data mining, we're usually given a bunch of training data points, right? So if we want to reduce the size of the data, we want to reduce the size of all training examples. So let's say we're given a set of n training points, which all of them are d-dimensional vectors. So let's say we apply A to these vectors to a low dimension m. Okay, reduce high dimension d to a low dimension m. And then the JL lemma guarantees that. Okay, so if you compute the pairwise distance in the original high dimensional space, and also you compute the distance in the low dimensional space after transformation, so you see that the distance will pretty much preserved. It's very close to each other. all right? So it means that, so let's say it have some very important applications. For example, if we consider classification, so let's say we have high dimensional data points, large scale high dimensional data points. Let's say we have two class classification problem, and the data are linearly separable. Because this JL lemma, it guarantees that we can reduce to low dimension. So the structure, the kind of distribution of the data is pretty much preserved. So it means that if originally the two groups of data points are linearly separable, after reduction, these two groups of data points are still linearly separable with high probability. So that's why we can learn a good classification model in the low dimensional space without worrying about the high dimensional data. So that is a very important implication of the JL lemma. And one thing I want to focus on, want to emphasize here is that in order to guarantee the pairwise distance is preserved up within this epsilon accuracy, this is the value for the reduced dimension. So importantly, this reduced value here is independent of the original dimension d. So here, this value is independent of d. So if you have very high dimensional vectors in the for the original data, you can reduce to a very low dimension to this value, independent of d. You can reduce to a very low dimension, can reduce the size of the data dramatically. Okay, so next, what kind of distributions will satisfy the JL lemma? So we'll talk about several of them. So the first is the Gaussian random projection. It's very simple. So just generate each entry is sampled from a Gaussian distribution with zero mean and variance is 1 over m. Okay. So here, we want to talk about the computational cost of transformation, right? So because the randomized algorithm, you first apply the randomized reduction, right? So this is the additional cost we will suffer. So we want to control that cost. So here, the computational cost of, by applying this Gaussian random projection to a data matrix X, d by m, would be n times d times m for dense matrices, and there would be number of non-zero entries in X times m for sparse matrices. So you will see that the bad news is that this computation cost is very high compared to some problems we will discuss later. So it's as high as solving those problems. So we don't want to use this. So that's why many research work has been proposed to try to accelerate this JL transform. So the first idea here is that using discrete distributions. So instead of sample the entry from the Gaussian distribution, you can sample from a discrete distribution. For example, you sample Aij from these probabilities is a positive or negative one of square root n with equal probabilities, or with this probability distribution. Okay, so the benefit here is this distribution is database friendly. It can be very efficiently can performed in a database environment, and also it replaces the multiplications by addition and subtractions. And later on, people designed a better approach. It can be applied more general, which is based on the idea of Harmonic transform. So the motivation here is that can we simply use random sample m coordinates out of the original d coordinates, right? So let's say we have original high dimensional d vector. We want to reduce to m dimension vector. So the naive idea, you just simply sample with replacement, right? You sample without replacement, or sample m coordinates. So you can implement this by using a random sampling matrix P, which is each row here with only one entry is non-zero, which corresponds to the sampled coordinate. And it's scaled by this value. The reason of scaling is to maintain that after transformation, the Euclidean norm square is an unbiased estimate of the original Euclidean norm square. But unfortunately, this is very efficient, by the way. But unfortunately, by Chernoff bound, we will show that the difference between the Euclidean norm would be not very small. So this is the term that appears in the JL lemma. And this is the additional term we have. So this is the infinity norm of x times the square root of dimension divided by the L2 norm of x. So let's think about an extreme case when x only concentrate on one coordinate. So infinity norm would be equal to the L2 norm. So this would be a very large value, this square root of d. So this makes this bound not very useful. So this random sampling is not a JL transform. Does not satisfy the JL lemma, unless this is very constant. But in general, it's not. So here, this issue can be addressed by this so-called randomized Harmonic transform. So let me first tell you what is Harmonic transform. So the Harmonic transform is defined for dimension which is power of 2. Okay. Let's say d here is power of 2, which is 2 to the power of k. So it's defined recursively. So with one dimension, h1 is 1, h2 is 1, 1, 1, negative 1, and h with dimension 2 to the power of k is defined using the h with dimension 2 to the power of k minus 1. Okay? Because this recursive structure, we can actually implement, calculate this transformation very efficiently. So this computation cost of applying h to 1x is d times log d. And here, this Harmonic transform is actually a normalized version. So we scaled this h to, with this dimension by the square root 1 over d. And this is to guarantee that the resulting H matrix is a orthogonal matrix that preserves the Euclidean norm of the vector. And then with this Harmonic transform, we can define the randomized Harmonic transform. So for one randomized Harmonic transform, we first apply a random D matrix, which is a diagonal matrix. And each entry is a random variable with either positive 1 or negative 1. Okay? So which is equivalent to multiplying each coordinate in the original x vector with this random variable, either positive 1 or negative 1. And then you apply the Harmonic transform, so you get the randomized Harmonic transform. Okay. So benefit, the good news about this randomized Harmonic transform is that we have this good property. So if we compute the infinity norm of the resulting vector, okay, times the square root of the dimension divided by L2 norm of the resulting vector, so it would be bounded by a very small value. So it's only log dimension divided by k. So this is actually what we want here, right? So we want to bound this term. We want to bound the infinity norm times the dimension divided by the L2 norm. And that is achieved by this randomized Harmonic transform. So randomized Harmonic transform try to equalize the magnitude of the entries in the vector. And the resulting transform would be would satisfy the JL lemma with additional log term. So this is the difference with this is the only additional log term compared to the original JL lemma. But this log term can be further removed. So in terms of computational cost, if we apply A to the data matrix X with n times d size, so this is the cost, which is n times d log of n. Okay, and compared to Gaussian random projection, we reduce m to log of n. So if n d is very large, this reduction could be very significant. Okay, so this is the second idea of using randomized Harmonic transform to accelerate JL transform. The third idea is using a sparse matrix. So in practice, we for the large-scale high-dimensional data, we usually observe that the data matrix itself is sparse matrix. So number of non-zero entries is much less than n times d. So we want to further explore that kind of property. So here, the idea is using a sparse matrix, in particular using the random hashing matrix. So here I use the same notation H, but it's a different thing, okay? So this D is the same thing. So it's a diagonal matrix. Each entry is a random variable, either positive 1 or negative 1. And this H matrix is M times D matrix, so which tries to reduce D-dimensional vectors to M dimension. So this H matrix is a sparse matrix. Each column, there is only one entry is non-zero. So the precision of the non-zero entry in each column is determined by a random hashing function. So let's say the H is a random hashing function that maps the index from 1 to D to index from 1 to M. Okay, so you apply this to the D coordinates, right? And for in this H matrix, for each column, the corresponding non-zero entry is determined by the corresponding the hashing function that maps that coordinate. So there are only D non-zero entries in the H matrix. So if you apply this HD to a vector, to a data matrix, the computational cost is only the number of non-zero entries in the data matrix. It's very efficient if the data matrix is sparse. Okay. But technically speaking, the random hashing here does not satisfy the JL lemma. So here we want to make it try to satisfy the JL lemma with additional a little bit additional cost. So the first idea is that in this paper, they also show that the random hashing satisfies the JL lemma only when this condition is satisfied, when the infinity norm divided by L2 norm is less than 1 over C, which depends on the epsilon. So actually, we can first apply randomized Harmonic transform to satisfy this condition, right? And then apply the random hashing. So a better idea here is using a block of random hashing. So instead of using one block of random hashing, we use S block here. So each block Q1 is independent random hashing matrix, which I introduced in the previous slides. And by carefully choosing the number of blocks S with this value and dimension, so each block here reduce D dimension to V dimension. So choose this value for this for the dimension of each block, and we guarantee that the resulting A matrix is JL transform, and that satisfies the JL lemma. And the computational cost of applying this A to a data matrix is number of non-zero entries in X divided by epsilon times the log term. So compared to the Gaussian random projection, is much more efficient, and compared to the randomized Harmonic transform, is also very efficient when the data matrix is very sparse. Okay, so that's the Jensen-Lindenstrauss transform that can help us to reduce the size of data matrix. The second one is the subspace embedding. Actually, is more general than the JL transform. So in the JL transform, in the JL lemma, we try to guarantee that the length of a fixed vector is preserved. But here we want to generalize this to a set of vectors, to an infinite number of vectors. So here, instead of having a fixed vector X, we have a fixed linear subspace, a subspace W, which is a subset of the d-dimensional vectors. And here we assume the dimension of this subspace is K. So it means that if you want to find the orthonormal basis, okay, at most you can find K independent basis. Okay, so we want A matrix satisfy this property to guarantee that for any vector from this subspace, so its Euclidean norm will be preserved within this accuracy. Okay, with high probability. So if A satisfies this property, is called subspace embedding. So subspace embedding implies some very nice properties. So here, if we use U to denote orthogonal matrix, which contains the K orthonormal basis of the subspace W, and if you apply this A, that reduces this dimension D, number of rows, to M. Okay, so originally this U, each column vector is orthonormal, and these columns are linearly independent. But if you apply this to M rows, and we have high probability that this resulting matrix still have full column rank. So these columns are still linearly independent. So if you calculate the singular value decomposition is very close to 1, if you calculate this matrix transpose times itself, is very close to identity matrix. So this makes that this, is very close to U transpose U. U transpose U is actually the identity matrix. Okay, so these are the nice properties will be used in the theoretical analysis of many randomized algorithms. For example, low-rank matrix approximation that I will talk later, randomized least square regression, randomized classification. Okay, so we can make a JL transform to be a subspace embedding. So if A is a JL transform, if we make this M value to be this order, the K, the dimension of the subspace, times the log term divided by epsilon square, and it's guaranteed that this transform is a subspace embedding. Okay? And compared to the original JL lemma, this is an additional factor here, the K times a log term. And also we can make the block random hashing or subspace embedding by carefully choosing the number of blocks and also the dimension of each block. And the computational cost of applying this block random hashing is again linearly to the number of non-zero in the data matrix X. Okay, so previously I mentioned that this random hashing is technically is not a JL transform, does not satisfy the JL lemma. But actually in this paper, they also show that random hashing is actually a subspace embedding with a constant probability. So if you're choosing the value for the reduced dimension to be this order, k squared divided by epsilon squared, and it's guaranteed that with this probability, the resulting the A matrix here is a subspace embedding. Okay, so the good thing about this random hashing is that the computational cost of reduction is only in the number of non-zero entries in the data matrix. So because this random hashing here, this is a sparse matrix, so I will refer this to sparse subspace embedding. Okay, so that is two kind of transforms. So next I will talk about another transform. So for the first two parts here, you will see that actually the transforms are generated independent of the data. So next I will talk about randomized reduction that will dependent on the data. So which is called column or row sampling in the literature. So I use the term column sampling. So column sampling, the idea is that so if you have a data matrix X, so you want to approximate with a smaller matrix. So instead of using some random reduction approach, so here we randomly select the columns. So we want to select the most informative columns from the original data matrix to approximate the large data matrix. So this is the column subset selection problem, and also the feature selection problem. So compared to the randomized reduction in the last two parts, the column sampling here is actually more interpretable because in some applications the features have meanings, right? So you want to select the columns based on the features, right? So the selected features, the columns have meanings. So the resulting algorithms are usually more interpretable. And how to do the column sampling? So as I said before, that uniform sampling usually does not work. So you don't want to simply sample the columns uniformly, right? So it's not a JL transform. So here I'll talk about a sampling approach, which based on the so-called leverage score. Okay, so this is a leverage score sampling. Okay, so let's say X is a D by M matrix. Let's assume that is a rank K matrix. So for this matrix, let's say we want to select M rows out of the D rows to approximate this large matrix. Okay. Let's say X has this singular value decomposition, U times sigma times V transpose. And from this, we can define the so-called leverage scores. Okay, so for each row, there is a leverage score, and that is defined the Euclidean norm square of the row of the U matrix. Okay, so for the first row, you compute the Euclidean norm square. That is the leverage score for the first row. So you can do this for all the rows, right? And then you can define a probability distribution. So you define probabilities for all the rows, which is the corresponding leverage score divided by the summation of the leverage score. And then based on this probability distribution, you can define a sampling matrix. So what you can do is, let's say you use I1M to denote the M indices that you sampled from the D rows, following the probabilities defined here. And then you can define a sampling and a rescaling matrix, A matrix. So this A matrix, each row, there's only one position which is non-zero, which corresponding to the selected index. Okay, and that's scaled by 1 over square root of M, which is the value of the reduced dimension times the corresponding probability. And then you can apply this A to the X matrix, so which is equivalent to select M rows, okay, and then scaled by this value for each row selected by this value. Okay, so so the properties of leverage score sampling. So if we make M value of the reduced dimension to be this value, which is similar as we see in the subspace embedding, which is k times the log term. And here we can guarantee that we have the same property of subspace embedding. So the leverage score sampling is actually a subspace embedding. So that is a key property used in many randomized algorithms. Okay. So, but the bad news is that although the leverage score sampling is more interpretable because we select the rows, select the columns, but the bad news is that the computational cost is very high. So you need to compute the top k singular value decomposition of the data matrix. But later on, we'll talk about randomized algorithms to compute the top k singular value decomposition of the data matrix, which can reduce this computational cost. Okay. So that's the leverage score sampling. Sample the columns, sample the rows based on leverage scores. But in practice, you may wonder, can we use random sampling? What kind of scenarios we can use random sampling? Uniform sampling. Is uniform sampling valid in some cases? Okay. So here, in the literature, people try to use the coherence mirror to characterize this. So in the leverage score sampling, we sample the columns based on the leverage scores. So if we have large leverage score, you will have a high probability to be sampled. But if the leverage score are uniform, so if all the leverage score are pretty much similar, equivalent, the same order, and then you can guarantee to use uniform sampling, right? So that will produce the same, pretty much the same result of leverage score sampling. So here in the literature, people introduce this coherence mirror to try to control the maximum of the leverage score. Okay? So this is the maximum of the leverage score times scaled by d divided by k. So if this coherence mirror is small, is constant, and is guaranteed that all the leverage score would be very similar, so you can use uniform sampling. Okay. So good news is that in many data mining and machine learning data sets, people have found that they have small coherence mirror. So in practice, for example, in the nice-run method that I will talk about later, we usually use uniform sampling because we cannot afford the leverage score sampling. It's very expensive. Okay, so that is the randomized dimension reduction part that reduce the size of the data matrix. Right? So that is the first step used in the randomized algorithms. So next, I will talk about different algorithms that we use this smaller sketch that we obtained from this randomized dimension reduction to solve some machine learning problems, some data analytic problems. For example, classification. For example, regression, for example, least square regression, k-means clustering, kernel methods, and lastly is the randomized algorithm for singular value decomposition. If you want to compute the top k singular value decomposition, and here is the randomized algorithm can help us to do that. Okay, so let's first talk about the randomized classification algorithm. Actually, the algorithms, the techniques presented here will be applied to the regression, but I will only focus on the classification problem here. So this is the optimization problem we are interested in solving the problem, right? So we have the empirical loss. We have the Euclidean non-square regularization, right? So this includes support of vector machines. This includes logistic regression. As Qihang present in the second part, for the optimization approach, usually we need to take this computation cost. Sometimes better, we have better dependence on the condition number, but generally we have n times d times the dimension times the condition number or square root of condition number, and times the log term. If the problem is smooth, the loss function is smooth, we have this computational cost. So if we have large-scale, high-dimensional problems, we still have a large component here, right? N times d. So this could be still very large. And here we want to utilize the randomized algorithm to further reduce this computational cost. So the idea is actually very simple. So let's say we have high-dimensional problems. The dimension, the d is very, very large. And also possible the number of examples could be very large. So here we try to reduce the dimension, okay, instead of the number of examples. So let's say A is a random reduction matrix, which can reduce d-dimensional vectors to m-dimensional vectors. So this m could be much, much smaller than the original dimensionality d, okay? And we apply that to the x data matrix, n rows, d columns, so which is multiply x by a, so we get the new data matrix, which is m rows, m columns, okay? So right now we have much smaller dimensionality compared to the original data. So data size is much reduced. And then we can solve the classification problem using the reduced feature vectors. So here, the optimization problem is pretty much similar as before, but we use the reduced feature vectors, the m-dimensional vectors, instead of the original d-dimensional vectors. And also we learn a vector in the reduced dimension, m-dimensional space. And for the random reduction matrix A, we can use JL transform, subspace embedding. And in practice, people have found that this randomized reduction for applied to the classification can get a model which can achieve very close performance to the optimal model we can obtain from the original data matrix X. But in theory here, we want to talk about some guarantees in terms in theory. So here, we want to answer two questions. First, the guarantee about the performance. So as I said, when we talk about the JL lemma, so if the, let's say, if you consider the classification problem, if we have two classes classification problem. So if the original data are linearly separable, and then it's guaranteed that after a reduction, the data are still linearly separable with high probability. So we can still learn a good predictor in the low dimensional space, right? So that is, under that assumption, we have this guarantee, the margin is preserved. Okay, so data is still linearly separable. And in this work, they also shows that if the data matrix X is of low rank, okay, and we can guarantee that the generalization performance is also well preserved. It's very close to the optimal model we obtained from the original data matrix in terms of generalization performance. But under this assumption that data matrix is of low rank. Okay. So the second question here we want to answer is how to recover an accurate model in the original high dimensional space. So this question is very important in some applications. For example, in some domains, the features have meanings. So if you work on some bioinformatics data, right, some gene annotation data, right? So the features correspond to genes. So those features have meanings, right? So you want to obtain a model in the original high dimensional space that can help you to understand the importance of the different features. So that's why here we want to obtain a model in the original high dimensional space. But originally here, if you solve this problem in the reduced space, you can only obtain a model in the reduced space, which is the m dimension, which does not correspond to the features in the original dimension, original space. So here we want to present two approaches. One is dual recovery, another one is dual sparse recovery. So dual recovery here is the work we presented at the 2013 Conference of Learning Theory, and later on we extend to the journal version here. In this year SML, we present a new approach, a better approach, to try to relax the assumption we made in the first work. Okay? So let's first talk about the dual recovery. So the motivation is actually from the dual problem. So as Qihang talked about in the second part, using the convex conjugate, we can turn a primary problem into a dual problem. Okay? So this is the convex conjugate definition. And this is the primary problem. We can change this into a dual problem. Right? And dual problem is defined over the dual variables. And for each example, there is corresponding dual variable alpha I. Okay? And this is a quadratic term, which is x times x transpose, which is actually the gram matrix in the mentioned talked about in the literature. So if you have, if you want to use a kernel method, you can replace this gram matrix with a kernel matrix. Okay. So if we solve the optimal, solve the dual problem, we obtain an optimal dual variable alpha star. We can easily construct the optimal primal variable w star, which is given by this formulation. Okay. So this is the data matrix x transpose times the optimal dual variable alpha star, and scaled by this factor. So from this formulation, actually, we have an important implication. It implies that the optimal primal solution W star lies in the row space of the data matrix X. So is this property we explore in the dual recovery. So in the dual recovery, instead of solving the primal problem in the reduced space, we solve the dual problem in the reduced space. Okay? So this is the dual problem. Instead of using the original data matrix, we use the reduced data matrix, which is a much smaller size. And after obtaining our approximate dual variable, which is the optimal solution to this problem, which is alpha hat star, and we use that to construct a model in the original high-dimensional space using this formulation. So this is X transpose times this alpha hat star. So by this formulation, we still guarantee that this W2 still lies in the row space of the data matrix. It's still the linear combination of the rows of the original feature vectors. Okay. So here, in terms of the reduction matrix A, we can use any subspace embedding as long as M, the reduced dimension, is this order. So R times log R divided by data divided by epsilon square. So this R here is the rank of the data matrix. Okay. So we have guaranteed that if the data matrix is of low rank, the rank is R, and with this value of the reduced dimension, which could be much smaller than the high dimension D, and we can guarantee that the recovered model is very close to the optimal model we learned from the original data X. Okay? Any questions so far? Okay, so let's move on. So this is the dual recovery. We recover the model in the original high-dimensional space without solving a problem using the original big data matrix. But you might notice that there is an assumption we need to make, which is actually the low rank assumption we make, low rank of the data matrix. So in practice, you may not have the low rank of the data matrix, right? So that's why we present another work to try to relax this low rank assumption. So that is the idea of the dual sparse recovery. Okay? So here we try to explore a new condition, a better condition. So in practice, we usually observe that the number of support vectors, let's say in support vector machines. So there's support vectors, right? So in practice, the number of support vectors usually much smaller than the total number of examples. So which means that the optimal dual variable is a sparse vector. Okay. Is this condition we explored in the dual sparse recovery? So here in the dual formulation, instead of solving this part, we add our L1 regularization term here. Okay. So this is the L1 norm on the dual variable alpha. Okay. And tau is the parameter, regularization parameter. So the idea is that let's say originally we have large-scale high-dimensional data. Okay, the alpha star is sparse, means that many examples are non-spot vectors. Okay, they're linearly separable. Let's say mostly are linearly separable. But after reduction, you could see that many examples maybe become a little bit difficult to be separated. So originally, examples are non-spot vectors, but right now may become spot vectors. So that's why we introduced the L1 regularization to avoid that, to try to push originally non-spot vectors are still non-spot vectors, okay? To enforce the sparsity in the optimal dual solution. So we add this L1 regularization into the dual formulation, we get optimal dual variable, alpha hat star, and then we reconstruct a model in the original high-dimensional space using the same similar formulation here, okay? And here, in terms of the theoretical guarantee, we show that we can use any JL transform as long as the value of the reduced dimension is this order. The S here is the number of non-zero in the optimal dual variable, alpha star. And with this order, and we guarantee that with high probability, the recovered model is very close to the optimal model we learned from the original data matrix X. So that is the idea of dual sparse recovery. And next I want to show you one slide of experimental results showing the dual sparse recovery indeed actually give us better performance than the dual recovery. So we did experiments on real data sets. with this number of examples, this number of dimension, and reduce to a different number of values for m, from 1,000 to 8,000. And here we show the dual error in terms of the regularization parameter we add here. So if tau is 0, and this is the original dual recovery approach, so if we increase the tau value, and actually we indeed observe that by increase the tau to a little bit larger value, we can get a smaller dual error and also a smaller primal error. Okay? So this is better than the dual recovery. And we'll at the end, I will talk about the performance of this randomized classification approach. Okay. So next, I will talk about randomized least square approach, least square regression. So least square regression is to solve this problem, find a W to minimize the residual. Okay. So here we consider over-constrained problem. The number of rows is much larger than number of columns. The computational cost of solving this problem is n times d squared. So if n is very large, solving this problem is still very expensive. So the goal of randomized algorithm is to reduce this cost to be much less than this order. The idea is actually also very simple. So if we have a random reduction matrix A, so we apply this A to reduce the original n rows to m rows, which could be much smaller than n. So we apply A to X, apply A to the B, and resolve the reduced problem. Okay? Because right now for the reduced problem we have m rows, so the cost of the solving the reduced problem is n times d squared plus the reduction time. So if the reduction time is much smaller than n times d squared, we would save a lot of computation cost. Okay, so in these papers, they study the problem in terms of the guarantee, theoretical guarantee, and also the computational time. So this is the conclusion. And we can use JL transform, we can use subspace embedding, sparse subspace embedding, leverage score sampling to guarantee that the obtained model have the residual which is within epsilon factor of the optimal residual, and using this total time, which is linear to the number of non-zero entries in the data matrix X times d to the power of 3. Okay? So if d is very small and number of non-zeros in X is very small, so this training time is much smaller than the originally the n times d squared. Okay, so next is a randomized k-means clustering. Okay, so k-means clustering is given a bunch of training data points, x1 to xm with d dimension. We want to solve this optimization problem. We want to find a partition of the data such that the data points in each cluster, the distance from the data points in each cluster to their mean is minimized. Okay, so the computational cost of a standard k-means is n times d times k times t. K is number of clusters we want to find. T is the total number of iterations for the k-means. Okay, so this is the linear to n times d. We want to further reduce this by using randomized algorithms. So still, idea is very simple given we have talked about the randomized dimension reduction approach. So let's say we have high dimensional problems, and we can use the randomized reduction approach to reduce the dimension d to m. So this should be m, which could be much smaller than the original dimension d. And then we solve k-means using the reduced features. And it's guaranteed that using this JL transform, using the subspace embedding, sparse subspace embedding, with this value, which is k times log term divided by epsilon square for the JL transform, for the sparse subspace embedding with this order for the value m, and we can guarantee that the solution we obtain for the k-means is within epsilon accuracy in terms of the optimal solution we can obtain from the original data matrix. Okay. An analysis of the approximation error of k-means is formulated as a constrained low-rank approximation problem in this paper. And actually, this is can be studied in the same framework as the low-rank approximation as we talk about later. Okay, so next I will talk about randomized kernel methods. So I think many of you probably know that in many, for many machine learning algorithms, data mining algorithms, we can use the kernel trick to make the linear model to be a nonlinear model. Right? So using the kernel trick, we use a kernel function. So the kernel function kappa that can measure some kind of kernel similarity between two examples. So let's say we are given a bunch of training examples x1 to xn. And we can compute the kernel similarities between all these examples that will form a kernel matrix K. Okay? So the ith row jth column is a kernel similarity between ith example and jth example. Okay? So this K matrix is a PSD matrix. But the computational cost and memory cost of using this kernel trick, this kernel matrix is n squared. So if you have large matrix, this n squared could be very large value. Right? So probably if you use the leave SVM, if you have large data for the kernel machine, it's very expensive to train. Okay? So here I'm going to talk about two approximation methods to reduce the cost of kernel methods. The first is the Nystrom method. The second one is the random Fourier features. Okay, so let's first talk about the Nystrom methods. So the idea is actually very simple. So we do not want to compute all the entries in the kernel matrix. We only want to compute the partial entries in the kernel matrix. So in particular, we sample, let's say we sample m columns. So let's say the kernel matrix size is n by m, right? Let's say we sample m columns, which is much less than n. Okay, so this denotes the sampled columns, and then the approximation can be simply computed by some matrix products. Okay, so in particular, if we let A, so here, okay, this L times this L denotes the selected columns. So if let A to denote the uniform sampling matrix, so we apply A to this K, so K times A, which denotes the selected columns, right? Which denotes the selected columns. So we only compute entries in these columns. Okay, so this is the B matrix, and then we can also apply this X transpose to the B matrix, which is actually this part here. This is small matrix, okay, which is L times L matrix with small matrix, which is C matrix. So if we compute this B matrix, this part is also null. And then we can compute the approximation, an approximation of the original kernel matrix by using these products here. Right? So this is a Nystrom approximation, which is this B matrix, which is this part, times the inverse, pseudo inverse of this small matrix square, this C matrix, and times the transpose of the B matrix. So here, this pseudo inverse, because C is a much smaller size, so we can compute it very efficiently. So computational cost of computing this approximation is L cubed plus n times L squared. So if L is small, if n is very large, so this is much smaller than the n squared. Okay? So this is the Nystrom method. So after, if we obtain this Nystrom approximation, we can apply this to any kernel methods. Okay, so here I want to talk about the application of the Nystrom approximation to the support vectors. So in the support vectors, as I mentioned earlier, in the dual formulation, you can replace the gram matrix with a kernel matrix to implement a kernel machine, right? But you don't want to compute the kernel matrix. You don't want to solve the problem using the kernel matrix. So here we can use the Nystrom approximation to compute the approximate kernel matrix. So here we use this approximation here, which is B times pseudo inverse of C times B transpose. So if here we calculate X hat here, which is B times C to the power negative half. And this problem is actually somehow very similar to the linear problem we have seen. Right? And the short feature representation is defined in this X hat matrix. So this X hat matrix is n rows, L columns. Okay? So this L could be much smaller than n. And then we reduce original kernel method into a linear method. Okay? And then we can use any optimization problem that Qihang talked about in the second part to solve this dual problem. Okay? And then we obtain a prediction model. So this is the application of the Nystrom method to the kernel machine. And here I want to talk a little about the performance. So here, actually, training time is reduced dramatically, which I didn't show here. This just shows the testing accuracy. So the first bar is a linear machine. The last bar is the performance, is the accuracy of the kernel machine. And the middle bars here correspond to the Nystrom application of the Nystrom method. I'm sorry. The application of the Nystrom method to the kernel machine. So you can see that by increasing the size, the performance of the Nystrom kernel machine is very close to the kernel machine. But actually, the training time is much reduced. So here, I didn't show the training time. OK, so that is the first method using the Nystrom method. Second is the random Fourier features. So the idea of random Fourier features is based on this so-called Bergner theorem. So theorem shows that for shift invariant kernel, K, so if shift invariant is only dependent difference between x and y, and if only if this function is a Fourier transform of a non-negative probability distribution. So it's a Fourier transform here. This P is a probability distribution. Okay, so based on this, we can generate a short feature representation for each example, such that if we compute the inner product of these short feature representations, we'll approximate the kernel functions. So here, this is the definition of random Fourier features. So instead of calculating this integral exactly, we generate a set of samples from this distribution, denoted by omega 1 to omega n. Okay? And now we project for one example x, and project x to this vectors. We get omega 1 transpose x to omega m transpose x. And now we apply cosine and sine function. And then we get this short feature representation with 2 times m dimension. OK, so right now, we reduce the kernel SVM, kernel problems, to a linear problem. So you can apply linear method using this short feature representation. Okay, so you can solve kernel SVM, for example, using optimization algorithms for solving a linear method, okay, without solving the original kernel method. Okay, so for RBF kernel, for example, if you want to use this kernel, you can generate these samples from the Gaussian distribution, okay, with the mean zero and variance gamma squared. Okay, so I talked about 2 approximation methods for kernel method. One is a Nystrom method. One is a random Fourier feature. So you may wonder how they are compared with each other. Which one is more effective than other? So here in the 2012, we studied the 2 approximation methods in a unified framework from the perspective of functional approximation. So we found that Nystrom methods actually use a data-dependent basis to construct a prediction function. But the random Fourier features use a data-independent basis to construct a prediction function. So in certain cases, for example, when there is a large eigengap in the kernel matrix, when the eigenvalue of the kernel matrix follows a power law distribution, for example, and we guarantee that the generalization performance of the Nystrom method is better than the random Fourier features. And actually, we also observe the same phenomenon in the real data. So here I show the performance on 6 UCI data sets, either in terms of the square error on the regression data sets or the classification accuracy on the classification data sets. So this curve is the random Fourier features, and this curve is the Nystrom method. So you can actually see that on all these data sets, the Nystrom method performs much better than the random Fourier features. The reason because Nystrom method you use the data-dependent basis, data-dependent way to reduce the data size. But random Fourier features use data-independent distributions. Okay, so so that is a randomized kernel method. Any questions so far? Yes.
You have W hat minus W star.
Yeah.
Bounded by normal W star.
Yes.
So what's the interpretation of this? How can we understand this?
understand, you mean this relative error in terms of W star? You mean the epsilon times the L2 of W star?
Is this W star the optimal solution from that optimization problem?
This W star is the optimal solution from the original formulation using the original data matrix X.
Yeah, so in this case, the estimated solution minus the true solution
Yes.
is unbounded by the norm of the original solution.
Yes.
So how can we...
How to understand this result, right? So simply, I just give you one sentence. So if you look at the JL lemma, right? So JL lemma only guarantees that the relative, Euclidean norm square is preserved with relative to the Euclidean norm of the original data matrix X. And here, this is a similar form. Right? Compared to the JL lemma, it's very similar, same form. Okay, so that is the why we end up with this kind of results. But in practice, if you can make this to be very smaller, it still guarantee very not very large recovery error. Okay, so next, finally, I want to talk about randomized low-rank matrix approximation. In particular, if you want to compute the top K singular value decomposition of a big data matrix. So this is the randomized algorithm to do that. So the goal for matrix X, n times D matrix, so the goal is to obtain this top K singular value decomposition. Okay, so the U hat, V hat are also normal matrices. Sigma hat is a diagonal matrix with non-negative entries. And the size of U hat and V hat is K columns, right? So the K is the target rank. So let's say you want to compute the top K singular value decomposition. So the best rank K approximation, we know that is given by singular value decomposition. We retain the top K singular values and their singular vectors, right? And here we want to design a very fast randomized algorithm to obtain such approximation, which is very close to the matrix X, and also the error is not too large than the optimal error we can obtain from the singular value decomposition. Okay, because singular value decomposition, this is the best error, but computing the singular value decomposition for big matrix is very expensive. Right? So we cannot perform better than this, but we want to control this epsilon to be very small value. So why low-rank approximation? So there are many applications in data mining and machine learning, right? Principal component analysis, spectral clustering, and many others, right? So randomized algorithms. So actually, there are some deterministic algorithms can help us to do this, like truncated SVD, which is just SVD, but that is way expensive for big data matrix. A better deterministic algorithm is the rank revealing Qihang factorization. The cost is n times D times K. So for large n, large D, this is still very large. And also there is a special method called Krylov subspace method, which can perform in this term, where this T multi denotes the cost of matrix vector product. So here, compare with these deterministic algorithms, randomized algorithm enjoys several benefits. So for example, speed could be much faster. Okay. So later on, you will see that actually when we apply the randomized Harmonic transform, let's say we have a dense matrix X, so the computational cost could be as fast as n times D times log of K. So compared to this rank revealing QR factorization, so the reduction could be significant if ND is very large. And also the output is more robust than the deterministic algorithms. And also can be path efficient. So if your data matrix is very large to be loaded in the memory, you do not want to load the data matrix several times into the fast memory. So the randomized algorithm is usually path efficient. And also randomized algorithm, as I mentioned before, can allow us to explore parallel algorithms. So here I present the very basic version of the randomized algorithms. Actually, it works very well in practice. So only 4 steps. The first step is obtain a smaller sketch using the randomized reduction that I talked in the first part, right? So apply the random reduction matrix A to the X to reduce the D columns to M columns. Okay, M is smaller than D. Okay, so you obtain a smaller sketch, and then you compute a orthonormal matrix Q that contains the orthonormal basis of the column space of the smaller matrix Y. Okay, so don't worry, this step can be computed using the Qihang factorization because the size of the Y is much smaller than compared to the original data matrix X. So this step can be performed very efficiently. And then you compute singular value decomposition of a very smaller matrix, which is Q transpose X. So Q here is M times M. Q transpose X is M times D, right? So this matrix only M rows, D columns. So if M is smaller than N, this singular value decomposition can be also computed very efficiently. Okay? So if you get this singular value decomposition, and we can form approximation of the X matrix using this. Okay? So we retain the sigma, we retain the V, and for the first matrix, U tilde here, we define Q times U. Okay? So, and we can guarantee that this is a good approximation of the original data matrix X. So the explanation here is that if the column space of the smaller sketch, okay, this is a smaller matrix, if the space spanned by the columns of the smaller matrix captures the top K column space of the X matrix very well, it means that if we project X matrix to the column space of the Q matrix, and this difference is very small, and here we this step computes singular value decomposition, and then we form the U tilde, which is Q times U, and we guarantee this approximation error is also very small. Okay, so this is the randomized algorithm that allows us, allows the smaller sketch to capture the top K column space of the original matrix X very well. So in practice, actually, it works very well. So there are several questions I want to answer here. First is, what's the value of M? Okay. In practice, you make in theory, you can imagine if you use JL transform subspace embedding, so this M would be dependent on K, K times the log term. So in practice, you can make M to be K plus a smaller value P. Okay? So in practice, you can set P to be 5, to be 10, which will give you very good results. So what is the computational cost? So here I just show you the case using the randomized Harmonic transform. So using randomized Harmonic transform, computing the top K singular value decomposition could be as fast as N times D times log of K. So compared to simply calculating the singular value decomposition, M times D times M, this is much more efficient for big data. And in practice, very accurate. So here I show you one result from the paper, from this paper. Right? So this y-axis is the approximation error in the log scale. The x-axis is the number of selected, the dimension of the value of the reduced dimension. Okay? So the red curve is the optimal error using the singular value decomposition. And this curve is actually using the error of the randomized algorithm. The other one is actually a quantity can be used to monitor the quality of the randomized algorithm. So you can see actually, because this is log scale, the error is very small. So other things, you can use power iteration to further reduce the error. So instead of calculating the rank approximation of the original data matrix X, you'll calculate approximation of this matrix. Okay? And also you can use sparse JL transforms, sparse subspace embedding to further accelerate the calculation. Okay, so finally I want to conclude this tutorial. So, so far we have talked about 2 different approaches for addressing big data challenge. One is the optimization approaches, right? So from the optimization perspective, we try to explore the properties of the function. Smoothness, strong convexity, to improve the conversion rate, to reduce the iteration complexity, right? Another approach is using randomization. Okay, so there we try to explore the properties of the data. For example, linearly separable. For example, low rank of the data matrix. For example, the optimal dual solution is sparse to reduce the size of the data. So we use the randomized feature reduction, randomized instance reduction. So in terms of the advantages and the disadvantages of the two kinds of approaches, so for optimization approach, the advantage is that we can obtain the optimal solution, right? So the disadvantage is that it still suffers from high computation and communication cost for big data. But for randomized approaches, okay, so the advantage is it could be very fast, so reduce the size to very smaller size. But disadvantage is that we still have recovery error. Okay, although we have the guarantee of the recovery error, but we still have this kind of error there. So one question we raised here is that can we combine the benefits of two techniques? Can we enjoy the advantage of the two approaches but not suffer from the disadvantages? So here in this year SMA paper, we actually present approach to do this. So we combine the advantages of randomized approach and the optimization approach. So the idea is actually very simple. So you use randomization first to obtain a good initial solution. Right? So here we use the dual sparse recovery approach to solve a reduced data problem. We get a good initial solution, and we use that to initialize a distributed optimization. So here I choose the SDCA that I proposed in 2013. So we try to reduce this distributed optimization, okay, using the good initialization we obtained from the randomized approach. And we observe that with only one or two epochs of, with only one or two communications, we are getting pretty much the same performance of pure optimization. So we save computation cost dramatically, but we obtain pretty much similar performance. So this is the results we obtained. So we did experiments on a large data, which is KDD CAP 2010 data, with this number of examples, this number of dimensions, very large value. So here we distribute algorithms over 10 machines, and we reduce this dimension to pretty much 1,000 dimensions. Okay, so the first bar here is the result, is the model we obtained in the low-dimensional space. Right? So we reduce the data, and we solve the primary problem in the reduced feature space, and we evaluate that model in the reduced low-dimensional space. The second one is the recovered model. By the dual sparse recovery approach, we recover a model in the original high-dimensional space. So you can see that we actually recovered model can increase the performance by about 2 to 3%. So the last bar here is the performance of the model obtained by pure optimization. You can see that there's still some gap, although they're close, like 2% gap there. So we want to further reduce the gap. So that's why we want to combine the randomization approach and optimization approach. So here we get an initial solution from the randomization approach and use that to initialize the distributed optimization and then run one epoch or two epochs. So you can see that we get pretty much similar performance, very close performance to the pure optimization, but in terms of running time, it's still very efficient compared to the pure optimization. And this combined approach is pretty much similar to the randomized approach in terms of computational time, but the performance is very close to the pure optimization. So that is all I want to talk about today. I want to thank you for attending our tutorial. So if you have any questions, I'm happy to take right now. No questions? Yes?
How can you explain that for the final slide, the performance are not as good? Because you are still working on the convex class of problems.
Yes.
You just change the net. So you are changing the initialization. But then afterwards, you run the same algorithm, but you say that at the end, you are not getting as good results or as a pure optimization. Why so?
So first, we don't change regularization, right? So here we use randomized approach to reduce the size of data. Okay, so by reducing the size of data, we gain the benefit that the training is very efficient. The running time is very small compared to the pure optimization. But the disadvantage is we get some error, so some gap from the optimal model. Right? So we don't change the regularization parameter. Yes. So
using the randomization step first.
yes.
I got it. But then I don't get why you are not getting as good results as the pure optimization.
Okay, so here I just show like 1 or 2 epochs of a path of the data. We get very similar performance of the pure optimization. That usually needs about tens of epochs, hundreds of epochs, yeah, to get the same performance. Okay, so if there's no more questions, thank you again. Both Qihang and I will be around. We can further discuss any issue regarding the big data problems. Thank you.
这你好牛
啊！
这你好牛，
什么好的？
这个方的都不会，说教教我。哎。
周先生，我有很多问题，所以。